Let's work through a problem here. I have a conducting rod with a uniform linear charge density. Uniform. This is length x. Let's make it L. Let's make that the x-axis. And then here I have some point, and we'll call this distance here z. And that's from the tip here. And the question is, what is the electric field at this point? We'll call it point P. So the electric field at point P equals what? First off, this uniform charge density, and so the total charge will make Q and over L. Now, since the electric field depends upon the distance, then I have a charge distribution, so I need to create a dq here. The electric field at point P is equal to, well, we assume that it's positive, and that therefore the electric field is going to be going in that direction. We'll make that the I hat direction. Because it is a one-dimensional problem, we could just get by with just saying that to the right is positive. So this is equal to K dq, so I guess it's the differential of the electric field, over R squared I hat. And and I'll probably say this in other videos also, when you're trying to figure out the direction, there are two techniques that you can go through. One of the techniques is you play strict adherence to the math. And the other one is that you think through the direction and then do the math sort of separate. R is the distance from here to here. X is the distance. I've said X is equal to 0 there. I could have chosen a different X, might make the math slightly simpler in one place, but usually making math simple in one place makes it more complicated in another. In other words, this distance right here is just this total distance minus x, so that's L plus z minus x. That's what R is equal to. Or we can say that R plus x is L plus z, get to the same place. So L plus z those are both constants here. I could, if I want, create another variable, but I won't. So because I have a differential here, calculus is going to be involved. So EP would be the k times the integral of dq over r squared. I hat's also a constant. dq, I know from this that lambda is equal to dq over dx. Therefore, dq is equal to lambda dx. So this is k times I hat lambda dx over r squared, and I have a value for r here, that's L plus z minus x squared. Lambda is a constant, so I can pull that out, so this is equal to lambda k I hat integral dx over L plus z minus x squared. And I'm putting L plus z in parentheses here just because to indicate that basically it's going to go together. There's no reason to expand L plus z out, at least at this point. I now have, in terms of a single variable here, x is going to go from 0 to L, because that's the smallest value of x, to the largest value of x. And I'm going to do a little u substitution. I'll let u equal L plus z minus x, and therefore du equals negative dx. I plug that in, and so I now have my electric field is equal to lambda k I hat times a negative now pops out front because of the negative sign there, du over u squared, and so from 0 to L. So this becomes negative lambda k I hat u to the negative 1 times negative 1. Technically divided by negative 1, gets you the same place. And so the negatives cancel out, so I'm left with lambda k I hat over u, which is L plus z minus x, from 0 to L. So I get lambda k I hat over L plus Z minus L minus lambda K I hat over L plus Z. Here the L's cancel out, so I'm left with lambda K I hat over Z minus lambda K I hat L plus Z. Probably been easier to keep this factored out, but I didn't do that, which is lambda K I hat L plus Z minus Z over Z L plus Z. The Z's will cancel out here. So I'm left with L lambda K I hat, because that's L on top over Z L plus Z. And lambda is Q over L, so that right there is just Q. So this becomes Q times Coulomb's constant, I hat over Z L plus Z. So now let's just check to see if this makes any sense. If Z becomes huge, then the denominator becomes large. In other words, if this is incredibly far away, so this point P is incredibly far away, this gets farther and farther away, so the electric field should go down to zero. So if Z becomes incredibly large, it indeed does go down to zero. Now the question is, if L becomes really large, well, as L becomes larger and larger, we should expect the electric field to become bigger, but that's not necessarily what shows up right there. So let's take a look over in this corner right here. So I have Q, K, I hat, Z, and then I'm going to go ahead and factor out an L. So ZL, 1 plus Z over L. And so as L becomes large and Z stays relatively the same, this term here goes to 0, and what we're left with is QK I hat ZL. All right, so we have that expression up there, and the question was whether this is legitimate or not, but recognize that if L becomes larger, so does Q, because we do have this uniform density here. And so we'd probably best to go back and look at that as in lambda L K I hat over Z L. L's would cancel. And so if L becomes bigger and Z stays constant, so Z over L starts getting closer and closer to 0, then what you're going to end up with is this lambda K I hat over whatever that distance right there is. And so that's the other extreme. Now I can't look at that and go, oh, well, obviously that's correct, but there it is anyway.